The Poisson distribution, it's also told like this. I will explain. This is what is written in book. I have told you the story in short framework, but the book is, you will find like this. What it means is that it's counting the number of successes in NT time. That is the NT. The rate lambda is assumption. So N0 means the number of successes in zero interval is zero. The process of independent increments. That means each are independent of each other. And probability NH, the number of successes in H length is 1, is nothing but lambda H plus order of 0. That means this you can consider is nothing but lambda H. This means this is something that goes to 0. And probability NH greater than equal to, that is number of events that can happen more than 2, more than 1 is 0. Is all 0. Small of H means it's 0. As H goes to 0, it becomes 0. That's the basic idea. NH means the number of successes in H time point length. Okay, that is NH. So our assumption was what? In each strip of length H, it follows a boundary distribution. That means it will either have 1 success or 0 success. So it is exactly what it's saying. It is saying it means that probability NH greater than equal to 2 means the probability of more than 2 successes happening in this n of length H is small o of H. Small o of H means as H becomes smaller and smaller, this goes to 0. That means in some sense, for very small H, the probability of 2 or more events successes happening in the H interval length is 0. That's what it's meaning. That means either 0 success will happen or 1 success will happen. Now, what is the probability of 1 success? It's P, right? And you have assumed, if you remember, that P by H is equal to lambda. So it's P is equal to lambda H. So therefore, it's assuming that as H goes small and small, the probability that success will happen is P. That P is assumed to be lambda H. So all the 3 conditions are written in a different way out here. Plus order of H means as H goes to 0, this becomes 0 and 0. Therefore, the last 3 conditions are equivalent to the fact that it's Bernoulli, it's independent Bernoulli, Xi are all independent Bernoulli, and in the limiting framework, the average is lambda in unit time, the average number of successes. The last 3 points are telling that only. The last means that small of H means what? Small of H means as H becomes smaller and smaller, that small of H means it becomes 0. So the last line means that the probability in that small H interval, number of successes that is 2 or more, is actually going towards 0 as H becomes smaller and smaller. In other words, it's telling that the number of successes can be either 1 or 0. That is what it's telling. So in some sense, actually, nothing but it's telling the terms in mathematical and much more. I explained it in a different way, but it's the same thing. So this is called Poisson process. It's a direct, it's a direct extension, continuous version of the Bernoulli process. Now, if we ask the same question, so the proof is given over here, the same proof I asked, the same proof I explained it to you. If I ask the same questions, 5 questions here, that how many events will be there, not in n time or t trials, but till time t, how many successes will be there? That is done by Poisson, lambda t. Right? I have explained it to you. Now, if I ask you how much time it will take to get to the first arrival, in this case, it was how many trials it will take, right? But here we are extending to time, how much time it will take. So we will see it's nothing but exponential when we will teach you exponential, okay? Or I can show it to you today. Let's see. The number of time to get to the first success is nothing but the exponential. That means exponential is nothing but the geometric continuous version, geometric distribution continuous version. If I ask you how much time it will take to the first arrival, that's exponential. Similarly, if I ask you how much time it will take to get to the rth arrival, the first r, it will be sum of exponential, which will be gamma. So gamma is the continuous version of negative binomial. Okay, and the beta is similar like hypergeometric. So we will say beta has a very interesting relationship with Bayesian distribution. Bayesian statistics will ditch that stuff. But beta distribution is used to model the probability. It's a model for random variable of a probability. We'll see why it's important. So the hypergeometric extension is beta almost. So beta, binomial, all these things are totally related to each other, and hence hypergeometric. These 3 things are related to each other very closely. So if I want to, cover all the things up, you will see that Bernoulli process ka number of arrivals in the first n or t trials is binomial. Similarly, Poisson process ka number of arrivals or success in the first t time is Poisson. If I ask the interarrival time, it becomes geometric. Here it becomes exponential. If you ask the number of trials to get to the first r success arrivals, it's negative binomial here, it's gamma here. And hypergeometric and beta are corresponding extensions also. Did you understand the connection, guys? We have not proved it yet, But this is the entire connection that is happening behind the screen, which the story that is there in the probability distribution, the connection, which you're not told. Poisson to exponential is not happening, it's a Poisson process. Okay. So exponential is nothing but number of time. It was in geometric, it was number of trials. Here it is number of how much time. It's a continuous version of trials to get to the first success or arrival. In geometric, it was number of trials to get to the first success. In exponential, number of time to get to the first number of how much time to get the first arrival. So this is, I will prove it. Okay, it's not proved it yet, but I will prove it today only. But this is a relationship. Okay, so in what I told is that geometric is we will prove it that box of exponential is geometric. Box is nothing but the discretization of the continuous random variable, and gamma ka box is also negative binomial. These things are really there over. Okay, it's a connection between these things. Essentially, we are moving from binary process, which is a discrete process, to a continuous process, which is a Poisson process, and we are asking the same questions. The trials, number of trials becomes how much time. And if you ask the same questions, you get different answers, and hence the connection. The binomial Poisson connection is there, the geometric exponential connection is there, the negative binomial gamma connection is there. They're just same things, but they are told differently. This is the connection that I want to teach you today. And with this, I will move ahead to the standard continuous distributions that we'll be learning next week. Okay. So this was the connection point between standard discrete and standard continuous. The Poisson process and Bernoulli process relationship tells you so. This was the, the connecting point between these two, modules of classes.